Sorry, so I will wait for you. Sorry, we have to wait for the signal before starting. Here. Is it okay? Okay, so good morning. I'm Carla Chiesserini from Politecnico di Torino, and as you know, today we're going to look at the vehicular use case for 5G. So as Professor Casetti said, this is one of the most important use cases. And although I don't know if it's so relevant to you in India, we were indeed discussing with Professor Casetti, you have such excellent drivers that probably you don't need that. But it could be a revolution, you know, because it means that we could have autonomous vehicles that are connected, that talk to each other, and actually enable several useful use cases. And we're going to review some of them. I would like just to point out this sentence here that is from the US administration for traffic safety on the highways that says that by 2023 we should have that 100% of the new vehicles should be equipped with V2V communication technology. So this is important because, to tell you the truth, the idea of having cars that talk to each other has been around for quite some time. But it has been when this administration has announced that they will suggest the implementation of V2V communication that actually things really sped up. And now we have car manufacturers that are really interested in these new technologies. They are experimenting the technology. So FCA, BMW, Volvo, many Toyota, many different car manufacturers actually look at 5G and in general at connected cars as a very important technology for their products. So let's consider first of all what we are talking about. It is our cars, and we know how a car works more or less, but what should be different when we consider that these cars are communicating with each other. So what is different from the communication point of view with respect to other network nodes, more traditional network nodes that we are dealing with? Well, first of all, the mobility of the vehicles. So the vehicles clearly follow a road, and typically they should also obey some rules, right? So there is no mobility like in the human scenario where people move randomly around, like in a square or in a mall, but there is a constrained mobility along roads. And also you can model the mobility of the vehicles based on the traffic signals, as well as the so-called micro-mobility, that is the interaction between cars. So if a car in front of you brakes, you should slow down or brake as well. So this is actually a very important aspect of our systems, especially when you go and evaluate the performance of your system. You have to make sure that the mobility that you are simulating or considering, it is realistic. Then we have the network topology. Well, the network topology is peculiar because clearly it changes very frequently, right? Because we have our vehicles, they will communicate with each other, but the communication link that they establish is going to last for a short time. So there are studies that have shown that the average duration of a communication link between two vehicles is about 1 second, 1 second and a half. So that's very short. So the topology changes very frequently and unfortunately suddenly. So that's an issue for us. Resources. Well, this is a good news because the resources are not so limited as in other systems like sensors, right? Here we may have a quite powerful CPU, memory, and also energy is not that important because you have some availability in your vehicle. Localization. Well, this is an important aspect. Localization means that our vehicles are supposed to have a GPS aboard. Now, this is quite straightforward. Many cars already have the GPS. So we could consider that they have knowledge of their position, and also they have a common time reference. But we will see that actually it is not, let's say, perfect, the synchronization among the vehicles. And also there are many cases where unfortunately you are not in visibility of enough satellites. So you do not get your position correctly, and you may have very significant errors in your position. So under ideal situations, we can consider that the position is always known to cars, but in reality, we know that this is not entirely true. So this is, let's say, this scenario that we are dealing with. What we are going to look at during this class is basically, the applications and services that our connected cars should support, and then the standards that we have and that also are going to change in the future. So we will look at the future and see what should change, what we expect that will be modified. As you can see from here already, we are going to look at different standards, meaning that there is a US-based standard and a European-based standard, and we look at both of them to have a complete picture of the situation. So let's start with services and applications. The first keyword that I would like to introduce is ITS, because you find this keyword everywhere when we have a scientific paper on a vehicular communication, and also in the transportation field. It has become very, very common. So it is ITS, Intelligent Transportation System. So ITS is indeed the whole system composed, of course, of cars, but also roads. So the road infrastructure, bridges, traffic signals, so traffic lights, for example. And clearly, considering that our vehicles are going to communicate with each other, there is also the communication aspect to take into account. So our vehicles will clearly implement some applications, and in our view, these vehicles will be connected, so able to communicate with each other, as well as with the communication infrastructure. Notice that the road infrastructure, like traffic lights or bridges, can be equipped with radio interfaces, and they may become a communication infrastructure as well. Okay? So here is just a graphical representation of our ITS system. So as you can see, basically every element here in this scenario has got a radio interface. So not just the vehicles, but as we were saying, also we can have buildings with antennas, as well as road infrastructures that have got a radio interface as well. So given that we have this intelligent system, the vehicles that run on this scenario are equipped with several different devices. This is the ADAS view, where ADAS is the acronym for Advanced Driver Assistance System. And this is the vehicle that already exists and that we expect that will be widely adopted, so very popular in a few years. So indeed, vehicles have got already several sensors, okay, especially you know, the luxury class category of vehicles. But more and more vehicles have got the radar, camera, LiDAR, ultrasonic sensors, and of course GPS and the availability of maps. But among these, there is also what is called V2X wireless sensors. This is, as you can see, the view of Qualcomm, that is this big company in the US based in San Diego. So communication is the radio interface is seen as one of the sensors aboard our vehicle. So if we have such vehicles, what is the result? Well, the result is that through all these sensors, the vehicle can acquire knowledge about this environment that is around the vehicle itself, right? Through radars, we can actually detect obstacles and other vehicles that are close by. Through communication, as we will see, we will be able to acquire more information, and not just about our own neighborhood, but also about the neighborhood of our neighbors. So the wireless sensor is called like that because it is actually the communication part that gives the possibility to the vehicle to build its own electronic horizon. So it acquires knowledge of what is around by putting together the information that it collects locally through its own sensors, as well as the information that it acquires through the communication, so about collected by the sensors of the vehicles around. So it's an extended vision, an extended model of the environment that we can obtain through the communication sensor. And the expectation is that our cars will process up to 25 gigabytes of data per hour. So that's what we expect it will happen soon. That is huge. It's a lot of data. So you can understand the potentialities that is there, right? Lots of data that you can dig and use in order to build applications for your vehicles. And indeed, research is going along this path. How to exploit all these data in order to improve the traffic safety, traffic efficiency. So, safety. This is indeed one of the most important use cases that we have. Why? Well, because, of course, safety is about people. And, for example, in Europe, we have that car accidents are one of the major death causes, along with cancer and heart attacks. So, clearly, the European Commission has put a lot of money on projects that try to improve traffic safety. And the recommendations by the US administration for traffic safety, of course, is along the same direction. So we need to equip our vehicles with devices and to develop protocols and to develop applications in order to solve this problem. And notice that this implies also, let's say, a better applications for our vulnerable users that should be protected, better protected. And this is possible, indeed, if we enable communication between the vehicles, between vehicles and pedestrians, between pedestrians and infrastructure, and between infrastructure and the vehicles. Then we have transportation efficiency. Transportation efficiency is a very broad class of actually applications, different applications, because as you can imagine, is about making the traffic more efficient, and this, implies also, let's say, parking search, right? that parking search is an issue in many, many cities, and it is indeed one of the main examples that fall in this class of applications. Many things have been already done, I would say, even if we didn't have connected cars. So an example is the intelligent traffic lights. I don't know if you have them here, but you know, when there is an ambulance and the traffic light was red, it will turn green. This is a simple example. There are many others, but it can really improve traffic efficiency. So we are looking for solutions that further improve the situation and reduce the commuting time, daily commuting time for people. So there are many places where people spend a lot of time driving, and that's clearly bad for the people, for the economy. So we should reduce this commuting time for the good of everyone. Third class is entertainment. Entertainment is indeed important. Video on demand, video streaming for passengers, and you know, sometimes also driver tries to access emails and so on. So this is clearly important, and among these there is one application that is considered to be very, very promising, and that's multiplayer games. So the fact that our passengers will play games with other passengers that are in other cars. So this is thought by several people as a killing application, and indeed gaming is gaining a lot of popularity and therefore also relevance in terms of revenues. So let me then introduce a use case and an application that is a bit peculiar, let's say different from the others. That is the one of autonomous cars. We all know that autonomous cars are already there. There are some companies that actually have these cars. In Turin, for example, we'll have very soon areas where autonomous cars are allowed. And this means that, Turin is not that big advanced city, so if these things become real in Turin, it means that really we are almost there. Right? It's not Palo Alto, Turin is not California, but still we are going to have autonomous cars even there. So autonomous cars can exist clearly without any communication in principle. What you need is sensors, right? So radars, lidars, and so on, cameras, and then algorithms that control the vehicle based on the information that is available. So everything could be done without communication. But if we allow our autonomous vehicles to be connected, well, then we'll have several advantages, and we're going to look at them. Just before introducing the benefits of communication, just to complete, let's say, our vision of autonomous cars, let me go through very briefly this classification that are the different levels that are expected for the autonomous cars, from 0 to 4. Now, let's say that we are basically here in terms of largely widely adopted cars, because many vehicles already have these applications that assist the driver during maneuvering, for example. So that's pretty common. What we are expecting will be very popular in a few years is level 3 and 4. That means vehicles that are really autonomous and do not need the intervention of the human driver, although the human driver will be there all the same. But in level 3, basically, in most of the situations, the vehicle will be able to drive itself, and except in difficult situations, complex situations. In level 4, it should be able to drive itself under any condition. So even if the human driver is there, here we are really at the concept of autonomous car that we have in mind. And as you can see, the target is to reach level 4 by 2020. That is basically tomorrow. So this expectation to me seems a bit optimistic, but you never know, right? It depends on regulations. If regulations speed up, then you can really be there by 2020. So this is happening. Well, this is the main message. So as I was saying, autonomous cars are not necessarily connected, but if they are, well, then we can have several additional services for these kind of systems that are extremely important, that are going to improve safety and traffic efficiency. What are they? These are some examples that actually have been defined within a European H2020 project called 5G car. So the first one is cooperative perception. This is also a use case that is mentioned in the 3GPP standard. So it is not just envisioned by these European projects, but is commonly acknowledged as a very important service. So cooperative perception is basically what we were talking about before. The ability of our cars to acquire information from others, perform data fusion, put everything together, and build this electronic horizon of what is in the area that is nearby the vehicles. Then you have cooperative maneuvering. Now, once you have this electronic horizon, your autonomous vehicle could indeed build on top of that this second service. Cooperative maneuvering means that you are going to take into account what the other vehicles are doing before deciding what you should do in terms of movement. And actually, ideally, you should be able to exchange, share information and also the intentions that you have for movement with other vehicles, and basically reach a consensus on the movements of all vehicles that are nearby. Okay, so that's very, very complex. Not just in terms of communication, because as you can imagine, you need an ultra low latency for the communication, but also in terms of machine learning algorithms and approaches. Okay, it's not easy at all to make these decisions considering in real time what the others intend to do. It's a totally new area where you can actually, when we can work. So the third use case that we have here is the cooperative vulnerable user protection. As we were saying, this is also very, very important because unfortunately, many times the victims of car accidents are also pedestrians or bikers. So here we have the concept that our vehicles should communicate either directly with pedestrians, for example, or with cyclists and bikers, or with the infrastructure, and infrastructure talks with the vulnerable users in order clearly to avoid hitting the vulnerable users. So it's a very important use case. And then the fourth one is autonomous navigation. So autonomous navigation means that you should be able for the autonomous vehicle to come up with the best path that you are able to find. And in order to do that, clearly you have to use the electronic horizon that you have developed before. So you can see that the first use case that we presented, that is cooperative perception, is actually the basis to build many other cooperative services. And this is, of course, another one that you can build on top of that. So what you're going to do is to collect all the information that you've got from the other vehicles, your own sensors, use the electronic horizon, and at that point, since you have all the information related to the road topology, related to information, roadworks that may be there, related to the presence of other vehicles in the areas nearby, then the autonomous vehicle can clearly find the most efficient path that can be found. And one thing that I would like to add about that is, of course, in this case, you need to use detailed maps of the area where you are moving. And the maps that we are going to use clearly are not the ones that humans typically use, right? So this is the kind of map that we use when we have to look for a place. But this is not the kind of maps that an autonomous vehicle can process. So you will need something better than that, something very different. And this is an area of research per se, how to develop maps for our autonomous vehicles that are detailed enough and that clearly can be processed very quickly by our autonomous vehicles. We are not going into the details of that, but just to say that there is a research area that's actually focusing on these aspects. And then we have remote driving. So this is another use case that is explicitly mentioned by also 3GPP, and it consists in the ability to drive a vehicle remotely. It is very useful in case you have disabled or elderly people that should go around with a vehicle, or to drive a vehicle that has to cross dangerous areas. So clearly you cannot have a human driver there, and you have to drive the vehicle remotely. So this is possible if you have, again, of course, machine learning algorithms, but also reliable communication. And that's where, let's say, our work should be focused on. So given that we have all these different use cases, all these different situations, and we saw that they might be very, very useful in many conditions, and that all of them imply communication because they are cooperative services. And here what I tried to do was just to classify, let's say, the different applications and to state the requirements for us that are there. So first of all, safety critical. Well, whatever is safety critical clearly requires a very low latency. And when we say ultra low latency, this means that the latency of the communication should be between 3 milliseconds and 150 milliseconds. Now, this is extremely hard to achieve, extremely hard. Data rate, it may go from 50 megabits per second if we are going to exchange these sensory data that have been pre-processed, and therefore, let's say they are already low resolution data, to 1 gigabit per second as a data rate if we are talking about the high resolution data. And again, these data rates are extremely high. So with the current technology that we have, still we cannot achieve that. Okay? Transportation efficiency and autonomous cars, well, clearly in this case we have very diverse requirements, because if we are talking about traffic efficiency like parking search, well, then there are no such strict requirements in terms of latency. But if we are talking about autonomous cars like cooperative maneuvering, then again we are in the order of milliseconds. So very diverse. But in general, here we will not require very high data rates. And then if we consider commercial applications like entertainment, well, here clearly the requirements in terms of latency are looser, and also in terms of data rate. So order of megabit per second, but not as critical as when you have to exchange large amounts of sensory data. So all the use cases that we reviewed, speaking in terms of communication, they pose very significant challenges. And what we're going to look at is, as we said, the standard communication technology that we have today, and how these could evolve in order to meet these requirements. You already looked at CE V2X with Professor Casetti yesterday. We will see today what we can do by using as technologies based on the US standard and European standard, the communication that can occur through DSRC, that is the short-range communications, the Wi-Fi-like communication, to use simple words. Okay, so indeed, this is, let's say, overview of what we said and what we are going to look at. Given all these use cases, some of them are related to safety, others are related to non-safety. What is the communication technology that we should adopt? Well, this is still unclear. This is the main question that also car manufacturers are trying to answer. It is not clear. We have on the left the cellular technology, if you like, CE V2X. On the right, you have these short-range communication-based DSRC technologies that we are going to look at today. What is the best? As we were saying, we still don't know. It really depends. It really depends on what you care about, and it really depends which use case you are considering, which conditions you are considering. So what we can say a priori, for sure, is that the cellular solutions are going to be more costly. This is for sure. So cellular V2X, and in general, any communication based on cellular, you have to pay money, a lot of money, compared to what we are going to see today that is based on DSRC, that is cheaper. On the other hand, let's say that the cellular communication allows you to reach an extended range, radio range, while this type of communication, as the name says, are suitable for short-range communication. So in particular, V2V, but not for medium or longer range communications. It is true that answering this question and establishing, let's say, the boundary between the use of cellular and between the user of DSRC, it is a challenge that is quite interesting, and there are a lot of people that are actually working on this specific issue. So let's now look at these dedicated short-range communications technologies. DSRC, this is the acronym that is used in particular in the US. And they refer, as I was saying, to those technologies that at the physical and MAC layer recall the Wi-Fi that we use to connect to an access point. Okay? It is not exactly the same technologies as we will see, but it it is based more or less on the same ideas. So let's start with the architecture of the system. Well, the architecture is very simple. Indeed, the main actors are basically two: the vehicle and the road infrastructure. Now, vehicles are equipped this onboard unit, that is the communication interface, and they can talk to each other, as well as with this element, infrastructure element here, that is called roadside unit. Okay? Now, if you know Wi-Fi, well, the roadside unit may appear to you as an access point. And for now, we can think of it as an access point. But then we'll see that there is a fundamental difference with respect to that. It is not an access point when we look at the way these actors communicate with each other. Okay? But for now, to keep things simple, let's consider this as a sort of access points that have been deployed along the road with which the vehicle can communicate. So we will refer to this communication as V2V, vehicle to vehicle, and to this communication as vehicle to infrastructure. So now when we have a group of nodes, they may be vehicles, roadside units that talk, that communicate using this technology, the DSRC technology. Well, we say that they form a basic service set, and if they follow the US standard, well, the US standard is called WAVE, so we'll have a WAVE basic service set. This can be initiated by any node, either a vehicle or a roadside unit. So this is the first difference if you know Wi-Fi, because in Wi-Fi we still have as a concept the basic service set, that is a group of nodes that communicate with each other, but it must be initiated by the infrastructure element. Here can be initiated by the vehicle, no problem with that. The initiator of this group of nodes that are going to communicate together will transmit a service advertisement that is a sort of beacon message. So a message that is sent in broadcast, it can be heard by anyone. Okay? But this message is not necessarily periodic. It can be sent by the initiator whenever he wants or whenever he can. Okay? So now we have this group of actors, of nodes. And let me just stress that clearly within this group of nodes, as we said, both V2V and V2I communications are possible. But typically, V2V communications are used in order to implement, for example, safety applications. So for fast communication, direct communication between vehicles. So these are low latency communication, data exchange, but not with a very high data rate, not with this technology. While instead V2I is used between vehicle and roadside unit. In general, when you have services like, for example, entertainment, you need to download a video, you need higher data rates. Okay? And indeed, the roadside unit is typically taller, of course, than a vehicle. Then the antenna height is basically greater than in the other case. So the communication link that we can establish has got better quality and therefore a higher bit rate. So that said, let's look at the possible standards that we can have given the architecture that we introduced. Now, as we mentioned already, there is this WAVE US standard that is indeed the first that was issued. And it is very complete. It goes from the physical layer up to the application layer, as we will detail next. And it includes, as physical and MAC layer, this short-range communication that resembles Wi-Fi. Now, this standard has been quite successful. It has been the first to be proposed. However, it has got some issues. So the European Standardization Institute, ECE, looking at the US standard, well, thought, well, this is a good one, but there are several issues. We are late because the US started long before, but we could do something in order to improve what the US has done, and in particular to further develop the higher layers of the protocol stack. So that's how we come up with a second standard, that is the European one, that is now called the ITS G5. So the reality is that the US standard is really the basis, the one that was issued, and of course is it looked at as the main reference. But lately, the European standardization has contributed significantly to this technology as well. So we will start with the WAVE standard, that is basically the basis, and then see how the European activity has tried to enhance, sometimes improve the basic US standard. So looking at the US standard that, as I said, is called WAVE, one important thing to stress is the kind of communication that it aims at establishing. Now, this is the main difference with respect to Wi-Fi. If you know how Wi-Fi works, let me stress that this is the main difference, because here all communications are ad hoc. That means that the vehicles will communicate with each other in an ad hoc fashion, but also vehicle and roadside unit will communicate in an ad hoc fashion. So there is no access point, as I was saying before, in this architecture. The roadside unit is one of the nodes, as if it were a vehicle. Of course, it is not a vehicle, it's fixed, but there is no difference whatsoever in how these nodes communicate, no matter if they are vehicles or access points. So only ad hoc communication is foreseen in this case. If you do not know how Wi-Fi works, don't worry, you may actually neglect my comment, but just consider that this is, let's say, a peer-to-peer communication between our nodes. Okay, so this is the protocol stack. As I said, we have the physical layer, the MAC, but now the MAC is divided into sublayers, the lower MAC and the upper MAC. Then we have the usual LLC sublayer, and then we have network and transport block that, as you can see, there are two options. One is the default one, IP, TCP, or UDP, so nothing new there. But there is another option that is actually to go through this green block here, that is a network transport layer that has been designed specifically for short messages. And indeed, this acronym stands for the WAVE Short Message Protocol. Why? Well, because if you have short messages that need to be processed very, very quickly, you don't need to go through IP or TCP, but it's better to deal with these messages in a simpler manner. And then you have applications on top of this part of the stack that can be, as we know, safety applications or non-safety applications. This is the data plane that we actually focus on. Beside that, we have the management plane. And then there is this layer that is actually spanning through all layers of the protocol stack. So it's a vertical one that is related to security. And this means that security is very important and should act at every layer of the protocol stack. Now, looking at this representation, you can see that the different layers have different colors. Why? Well, because the wave standard is what defines the whole protocol stack. But if we look at the single layers, there are different documentations for each layer. In particular, the blue ones, so the physical and lower MAC, are referred to as 802.11p. And you may have heard of this, let's say, name, standard name. Then we have the higher layers, so the yellow one, the green, and actually the security one, that are referred as 1609 dot something. Okay? So this distinction is very important because the 802.11p, that is the physical and lower MAC, is the part of the wave standard that has been the most successful one. And it has been basically taken as is also by the European standardization. The higher layer, instead, are those that have been defined in less detail, and is where the European standardization has contributed most. Okay? So when you hear 802.11p networks, well, it means networks that adopt these levels of the standard. Okay? Now, let's look at, yes, please. So there is a header that is included in these messages. So there is, let's say, an encapsulation because you actually create a header that is attached to the message. But it is not, let's say, so complex as in the case of IP and a transport protocol. So it is one header only, so not two. And it is simpler than in the standard, let's say, stack IP, UDP, or IP TCP. But you still have a header for that layer of the protocol. Okay, did I answer your question? We will go back to that with a few more details. Hopefully by today, because we should complete these slides by today. So let me know if you have further questions also later on. Any other question? Of course, you feel free to interrupt me whenever you like. If I speak too slow, too fast, let me know. And any feedback is appreciated. Okay? Okay, so if there are no questions, let's look at the physical layer. I will be quick regarding the physical layer because this is indeed almost the same as the Wi-Fi A standard. For those of you who know, A is basically exactly the same except for the parameter settings that you have at the physical layer. For those of you that do not know 802.11a, Well, what is most important to know is that the technology that is used is OFDM, so quite advanced technology at the physical layer. And we are working at 5.9 gigahertz, basically. Okay, so different channels, but around this frequency of 5.9 gigahertz. This is indeed the frequency that has been identified for vehicular communication. So no matter if you are considering DSRC-based technologies like the ones that we are looking at this morning, or cellular V2X that Professor Casetti introduced yesterday, both should work at the same frequencies. And clearly, these may pose some challenges and coexistence issues in the future, right? Because if you have too many nodes with different technologies accessing the same frequency bands, then you may have problems. The bandwidth that you use is typically 10 megahertz for each frequency channel. But for, as we will see later on, in some cases, you can actually combine two frequency channels together and use 20 megahertz. But the default value is 10. So if you know Wi-Fi, this means that is actually half the bandwidth that you usually have in Wi-Fi frequency channels. The data rate ranges between 3 megabit per second and 27 megabit per second when you use 10 megahertz. And indeed, since with respect to regular, let's say, Wi-Fi, you have half the bandwidth. Well, if you remember the data rates that are possible in 802.11a Wi-Fi, well, these are half those data rates, because clearly you have halved the frequency channel. So this is the data rate, 3 megabit per second, that you will use typically for broadcast transmissions, while instead this is the maximum data rate that you can use for unicast transmissions. The physical layer parameters have been modified with respect to the Wi-Fi A standard in order to account for the Doppler effect. Since our nodes move a lot, clearly you have more problems, and therefore they have been, let's say, adjusted for that reason. But there is nothing new really in this case, because it's essentially the same as the Wi-Fi A version. As for the communication range, while different transmission levels can be adopted, and here you have some values. Greater values are possible if you have, for example, also a roadside unit. And depending on the transmission power, you can have different radio ranges. So the radio range varies typically from 200 to 500 meters. But what the US Administration for Traffic Safety said is that we should aim at achieving a radio range of 300 meters. So based on their studies, they have come up with this value as the most suitable one to support applications for vehicles. Clearly, you can reach this radio that has been recommended, but in general, let's say that if you are in a rural environment where the vehicle density is low, well, in order to have some neighbors, communication neighbors, well, you will need to have a larger radio range. If instead you are in an urban environment where the vehicle density is very high, well, then you may actually reduce your radio range in order not to have too many neighbors. So consider that this is the recommended value by NHTSA, but in general, adapting the radio range to the environment where you're moving is a good idea. Now, from the point of view of the spectrum that we are using, we said that we are working at 5.9 gigahertz, and that's true. And in particular, we have 7 channels there. So what the 802.11p standard says is that one of them, the central channel, should be used for control information. That means not just signaling, but in general the important messages. So this is the control channel, CCH. And indeed, it's the central one that is the, let's say, main frequency channel on which our vehicles should work, in particular for safety applications. While we have other 6 channels that are called service channels. So these 3 plus these other 3 channels. Those are service channels where we should not in general have service application messages, but other non-safety applications working there. In the case of service channels, as we mentioned before, we can combine 2 channels together in order to increase the bandwidth from 10 to 20 megahertz and therefore have higher data rates. Now, considering that in general, according to the wave standard, our vehicles should have one antenna, one radio interface, and given that we have several channels to work on, what can we do? How are we able to actually work on these channels if we have only one radio interface? Well, the choice is basically to have the time division. So you have a phase that is devoted to the control channel and another phase that is devoted to service channels. So this means that this, you can define a so-called superframe interval that is composed of these 2 phases, and then you will repeat this interval over time. The superframe interval is typically 100 milliseconds, and by default, according to the wave standard, we have that we will devote half of this period, so 50 milliseconds to the control channel and 50 milliseconds to the service channel. And then again, control channel, service channel, etc. So this means that during these 50 milliseconds, all our vehicles will work on the same control channel, will transmit, receive on that channel, and then during the second phase, any vehicle will select a service channel of its interest and work on that, depending, of course, on the BSS. So what the BSS is doing, what the initiator says, what are the service channels that are available for our BSS, and depending also on the services applications that work on the different service channels. So if you are more interested in an application that is actually using a given service channel, you can use that service channel rather than another one during this phase. Okay? So this is the choice that they made, and it is in general simple, a simple choice that also recalls what you have in Wi-Fi, because also in regular Wi-Fi, time is divided into superframe intervals, and actually we do not have in practice 2 different phases in the latest standards, but in the initial standard in Wi-Fi, in every superframe you could have actually a distributed contention-based access during one phase and a centralized access during the second phase. That was the initial idea for Wi-Fi. And basically they are taking exactly the same idea and apply the same idea to this vehicular communication. Now, in order to implement that, clearly you need some synchronization among our nodes, because all of them will have to work on the control channel at a certain point. So you need the nodes to be synchronized. As we said, this is a fair assumption if you have GPS, and GPS works fine for all of them. But if GPS does not work, then you are in trouble. And indeed, the standard, let's say, accounts for that, saying that only those vehicles that receive the GPS signal correctly can transmit on the control channel. The others cannot. They can just listen. That's it. In order to help nodes to have a rough idea of the synchronization, even if they do not receive the satellite signal, well, who has got GPS correctly and transmits a packet on the control channel, it should include in the packet header its own time reference, so that the other vehicles that are listening will receive this timing information. Clearly, it's not a very precise one, but at least they got an idea of the time, and therefore when they have to switch from control information to service information and so on. But only those that get the GPS signal correctly can actually transmit on the control channel. But this is clearly a first issue that we have. Okay? If GPS does not work properly, then this communication standard may not be so good for all our actors. Let me point out another couple of issues that we have here related to this structure of superframe, control channel, service channel, and so on. Let's consider this example. So we have a car accident here, and unfortunately, this car accident happens during the service channel phase. So the nodes are actually working on a service channel, and nobody is listening or transmitting on the control channel. So if you are a vehicle that is involved in this accident, you will generate a message, for example, to say a warning message, an alarm message saying there is a car accident at this location, right? So you would like to do that. But unfortunately, you cannot transmit your message at this time. You have to wait for the control channel phase. So this means that we have a delay that could be avoided, but given to this time structure, we just add some milliseconds of delay, if you like, unnecessarily, but given this structure, you cannot do better than that. So this is one first issue. The other issue is about resources utilization, because based on what we said, clearly we have that during the control channel phase, we are using only one channel among 7. So the other 6 are unutilized. And this is not good, clearly, because radio resources are scarce, and this means that you are not using all the resources that are there efficiently. So in this case, it is more about, let's say, the radio spectrum utilization performance. But still, we already found 2 issues with this standard that could be serious weaknesses for our system. So, excuse me, just to let how you prefer to proceed. If there is any break that you would like to take at any time, let me know. Okay, you're going to tell me when to stop, right? Okay, thank you so much. Great. So let's now move to the lower MAC layer. The lower MAC layer is very similar to, again, the Wi-Fi standard. And if you have some knowledge about Wi-Fi, well, that would be version E of the standard. But we are going to explain how it works anyhow. The peculiarity is that this is the representation of the lower MAC. What does it mean? It means that we have two MAC, let's say, interfaces, one working on the control channel and one working on the service channel. So we have two different instances of our MAC protocol for channel access, depending indeed on the channel that we are going to access. Okay? They work similarly, even if the parameters are different, but the way they work is the same. So in order to explain how it works, we will focus on one of them. Let's take the control channel. It doesn't really matter. So let's focus on one instance of the protocol. And as you can see already from this figure, we have 4 different queues, MAC queues, for this interface. And then these queues will be served according to certain rules. And clearly the packet that is selected, then it will go down to the physical layer to be transmitted. So how does this channel access work? Who knows how Wi-Fi works in general? All of you, or you know how Wi-Fi works? Very good. Any other student you know? All others do not know anything about Wi-Fi, right? You don't know anything. Okay. So let me start with some basic principles that actually apply to this radio interface as well as in general with slight modifications to the Wi-Fi technology. Now, the Wi-Fi technology is based on the so-called carrier sensing multiple access. You know what carrier sensing multiple access is, right? So it means that basically if you are a node, if you got a packet, well then, if you want to transmit a packet, first of all, you have to listen to the channel. If the channel is idle, then you can transmit. If the channel is busy, clearly you cannot transmit. Okay? Now, in Wi-Fi in particular, you apply this principle. But first of all, when we say that first you have to listen to the channel, you have to listen to the channel for a given time interval, okay, that is fixed by the protocol. So you have to listen to it for this given time interval. And actually, this time interval is not the same for everybody, because it depends on your priority level. If for any reason you have got higher priority, well then you can listen to the channel for a short time period, right? Because you are entitled to be, let's say, quicker than the others. If instead you have got lower priority, you will have to listen to the channel for a longer time period, right? Because in this way you will be delayed with respect to the others. Okay, now assume that you have listened to the channel for this time period that is assigned to your level of priority, and the channel is indeed idle. So as we said, this is the easy case, because at that point you start and transmit. Remember that we have only one radio interface. So if you transmit, you cannot receive, right? You cannot hear anything because you are transmitting. So it's a half duplex system. So this means that once you start transmitting, no matter what, you go on till the end of your packet transmission. So if you are colliding with the transmission, with the signal sent by any other node, you will not be able to realize that. Okay, you are completely deaf. You just transmit. Now, if the packet that you have transmitted is a unicast packet, it means that is intended for a specific destination, Well, if the receiver receives the packet correctly, it will send back an acknowledgement to you. So you know if the transmission was correct or not. If instead the receiver does not receive the packet correctly, it will not send anything. So this means that if you do not, the transmitter does not receive any ACK, clearly it means that its transmission failed. Okay? If instead the packet that you sent is a broadcast packet, so it's intended for all other nodes, no acknowledgement is expected. So you just transmit whatever the result is, you don't care, okay? You just transmit, that's it. Now, let's assume that your packet is unicast, so it's intended for a specific destination. If you receive the ACK, you are basically done and you are happy with that. If you do not receive the acknowledgement, well, it means that your transmission failed. At this point, you can retransmit the packet, but you cannot do that immediately. Okay? You have to recontend for the channel. That means that you have to listen to the channel again. And if the channel is idle, you are not entitled to transmit immediately this time. You have to extract a random time and wait for this random time before being able to actually retransmit your packet. So, first chance that you get, fine. If it's unsuccessful, then when the channel is idle, well, then you have to wait for this random time. And then you can retransmit. Okay? And you can do that till either your packet is successfully received or you have tried for a maximum number of attempts. And if you failed all the times, well, then you have to discard the packet. Okay? The other case that we have is when the transmitter has got the packet, he wants to listen to the channel is busy this time. So, unfortunately, you cannot transmit because the channel is busy. What are you going to do now? Well, wait. You have to wait for the channel to become idle, clearly. And also in this case, you cannot transmit as soon as the channel becomes idle. You have to wait for, again, a random time. If you wait this random time, then you are allowed to access the channel and transmit your packet. So to summarize, there are two main cases. When you are a transmitter and you've got a packet, you listen to the channel. One case is the channel is idle. The other case is the channel is busy. Now, if the channel is idle, as we said, you transmit. You transmit, and if the packet is unicast, if you receive an acknowledgement, you are done, finished. But if the packet is unicast and you do not receive the acknowledgement, then you have to try again. And when you try again, it's not enough to have the channel idle. You also have to wait for a random time. The second case is when the channel is busy. In this case, you cannot transmit. You have to wait for the channel to become idle. And also in this case, this is not enough. You need to wait for this extra random time before accessing the channel. Okay? So these are the principles based on which Wi-Fi works. And if you think about it, it resembles how people talk, how people have conversations. Why? Well, because first of all, we said it's a CSMA scheme. And this is indeed what we do when we talk to people. well, before talking, unconsciously, but we clearly listen and see if anybody's talking, because if someone is talking, we are not going to talk over the other person, right? That's usually impolite. And this is exactly what Wi-Fi nodes do. Second thing, if you are in presence of other people, more senior people than you, well, probably you wait a bit longer before saying something, right? So you wait if the senior guy is going to talk. Then if nobody talks and you have something to say, then you may say something. That's exactly what we do. And then consider the fact that you want to say something, but someone else is speaking, right? So clearly you wait for this person to finish talking. And then you do not immediately jump into the conversation and say something, right? Also, that is kind of impolite. You wait a bit, and it's a random time. You wait for a random time, and if someone else is actually faster than you, well, at that point, you have to defer your transmission and wait longer, right? So it's clearly a random time, and who gets the channel in that case depends on this random time, the random time that you decided to wait for. So when you explain Wi-Fi, it seems like a complicated protocol, but it's exactly how people talk. So just remember the basic rules that unconsciously we follow when you have conversations, and that's exactly how Wi-Fi works. Okay? Was it clear enough as a rough explanation? Okay. So basically, this is indeed what our nodes do. Also, our cars do according to this technology. So let's review now these points. As we said, when a node, when a car in this case, has got something to transmit, first of all, it will listen to the channel and for a certain time interval. The duration of the time interval depends on the priority level of the transmitter. Okay? If the channel is idle, then transmit. If the channel is busy, then you have to wait for the channel to become idle, and then, as we said, this is not enough. You have also to wait for this random time. And the time value actually that is extracted by our transmitters, also this time value will depend on the priority level of the node itself. Okay? If you have higher priority, then you wait for a short time. If you have lower priority, then you wait for a longer time. So basically, low priority nodes, low priority transmitters are delayed more than others. Once you get hold of the channel, well, you can transmit. Okay? You can say something. The other peculiarity of this scheme is that you can talk for a given time period. It is called transmission opportunity. So you have a certain time assigned. You won the channel, fine, and now you can transmit, but for this transmission opportunity, that is a given time interval. And again, it depends on your priority level. Okay? It is not, let's say, let's leave out the details, but anyway, the fact that when you transmit, you get hold of the channel, you are entitled to speak, and you speak for this given time interval, it means that all transmitters that have got the same priority level will actually be treated in a fair manner, because all of them will have the same opportunity to speak for the same time interval. So this is called temporal fairness, because all our transmitters will be indeed treated in a fair manner, meaning that they will talk for the same amount of time. And then, as we said, if the packet that you transmit is unicast traffic, you should expect an acknowledgement. Otherwise, you should try again and retransmit the packet if the acknowledgement does not arrive. Instead, if your transmission is broadcast, no acknowledgement is expected. So these are the main points of the communication. Are they clear? Okay, very good. So if you like, we can stop here. Sorry?
We can go for a break.
Okay, okay, great. So we will go back to the Mac with more details later. But for now, think about also what we said, and if you have any questions, please feel free to ask when we come back from the break. Okay? Thank you.
So the key is arranged outside.
Hi, Chetna. How are you? Good.
It's really nice to meet you after a long time.
Very, very nice to meet you. Sorry. To resume what we said, so we have two protocol instances, one for the control channel and one for the service channel. And as we said, for the control channel, we have 4 different queues, right? So we talk about Wi-Fi, and we review these steps that are the steps that should be followed by a car that has got a packet and it wants to transmit this packet. Now, we notice that several parameters here that are used depend on the priority level of the transmitter, right? So what is this priority level? Where does this come from? Well, if we go back to our picture, it turns out that each of these queues will indeed store traffic of different priority levels. So the 4 queues correspond to 4 different priority levels. And this means that each queue will be basically a protocol, a sub-protocol instance that will try to access the channel following the rules that we listed here and using the parameters to determine this time interval or to determine the random time that correspond to the priority level of the queue. Okay? So for the control channel, we have, as we saw in the picture, the 4 queues, and each of them is labeled in this way. Access category 0, access category 1, 2, and 3, and each of them, as we said, has a different priority level. Each of them will behave as a node, as a transmitter, right, independent of the others, even if they are within the same MAC interface. So everyone will play its own game, basically, and trying to access the channel whenever there is a packet in the queue to be transmitted. Now, the parameters that are involved during the channel access and that we mentioned also before are the following. They are associated to each queue and basically get these names. So this is that is called the arbitration interframe space, is the time interval that you use in order to assess whether the channel is idle or busy. Okay? So the name of that time interval that we mentioned is arbitration interframe space, and the acronym that we use is AIFS. So this means that the highest priority queue, when it has to transmit a packet, you will listen to the channel for a time equal to the AIFS 0. That is the shortest one, and so on for the others. CW mean and CW max are instead the extreme of the range of values from which you extract the random time. So we said that also the random time depends on the priority level that the transmitter has got. So indeed, this random value is extracted from a range of possible values, and the minimum is basically 0. The maximum is set to this value CW. So this is a big tricky here, because the minimum, remember, is always 0 of the range. This is the maximum. The CW is the maximum value of the range. Why do we have here minimum and maximum? Well, because this is the maximum value of the range, so the right extreme of the range, that we use the first time that we try to access the channel. If we need the first time for a packet to extract this random time, this is the time interval that we will use, 0 CW min. If the packet fails, and the packet was unicast, and we need to retransmit the packet, as we said before, again, we are going to need another random time. Now, this new value random time will be extracted from a range of values that is, again, from 0, because the minimum is always 0, and the right extreme of the range will be double this value. If we fail again, and we have to retransmit this packet again, we need another random time that will be extracted from a range of values that goes from 0 to the right extreme that is double the previous one, and so on. So this means that every time you need to extract a random time for a packet, you always double the range of possible values that start always from 0, and they are larger and larger, okay, as a range of possible values. Larger and larger till this maximum is achieved, okay, so it's reached. So once you reach this maximum value for the right extreme of your range, you cannot go beyond that. If you need to extract more another time a random value for your packet, well, at that point you will still use 0 CW max, because you cannot go beyond that, okay? And finally, we have the transmission opportunity value. As we said, when we get hold of the channel, we are entitled to transmit for a time interval that is called transmission opportunity. The transmission opportunity duration is defined by this parameter that again depends on the queue, on the priority level of the queue that we have got. So, to summarize, every basically queue behaves as a station, as a transmitter, possible transmitter. Whenever there is a packet in the queue, it will act by following these steps, and for these parameters, it will basically use the values that are associated to that priority level. Okay, is it clear enough? So let me just comment on this CW mean and how the extreme right value of the range evolves in the following slides. So we'll go back to that and repeat this concept. But let me first just show a graphical representation that highlights the impact of the arbitrary interframe space. So the interval duration during which we should listen to the channel and assess whether the channel is idle or busy. So as you can see from this representation, the duration of this time interval has indeed an impact on the channel access. Because if a queue has got a packet to transmit and it needs to listen to the channel in order to see whether the channel is idle or busy, it will have to listen for this time, as we said. And if you are a high priority queue, this time is shorter. If you are a lower priority queue, this time is longer, right? So clearly, the queue that has got the higher priority and that is using the shorter time interval will be able to access the channel before the others. So indeed, setting properly this parameter helps to maintain the right priority among the queues. Okay? And here is a similar representation for the random time that is also called bake-off time. So again, if you are a high priority queue and you have set your CW mean to a small value, let's say 3, this means that when you extract your random time, you will extract it from 0 to 3. So it must be a very short time because you have no other possibility. It's either between 0 and 3. So you are going to extract a short time necessarily. If you've got instead a CW mean that is equal to, let's say, 31, well then you may extract randomly a time value that is between 0 and 31. So statistically, you are going to extract a random time that is clearly longer. So what happens? Well, the high priority queue, we will have to wait for a short time. And therefore, it will access the channel quite soon. While the other one will have to wait statistically for a long time, and therefore, it will be delayed. Okay? Now, about this random time that we were, let me just jump a bit. No, sorry. Let me go back. So I hope I had a slide on that. But about this random time that we said. So we mentioned that we always double the range of values whenever we need to extract another random time for the same packet. Okay? So we said the first time that I need to extract a random time for a packet, I will use 0 CW mean. If the packet is unicast and fails, well then the second time I'm going to use 0 and a value that is twice CW mean. And then again the third time I will use 0 and a value that is twice the value before. Now let me explain why the standard says that a transmitter should do that. Because this access protocol is clearly contention based, right? Everybody contends for the channel, and depending on priority and luck, you get the channel and transmit. Now, if you transmit and you fail, there are two reasons why this may happen. One is, unfortunately, there was an error on the channel. So due to bad propagation, your signal to interference ratio at the receiver was too low. The receiver could not basically decode the packet because the useful signal got faded, and unfortunately the received useful power was too low. That's one possibility. You cannot do anything about that because it depends on physical layer propagation issues. So at the MAC layer, you cannot do anything. But the other reason why your transmission may fail is because you actually collided with another signal. That means that two transmitters got the channel at the same time, and unfortunately the receiver was exposed to both signals. So the two signals reached the receiver at the same time, and the receiver could not basically extract the useful information because there was this strong interference coming in. Now, the MAC protocol, in this case, should do something about that, right? Because this is due to channel access, so you could design the MAC in order to avoid such a situation. And indeed, doubling the range of values for the random time is done for this goal. That is, try to avoid collisions between transmissions. Why? Well, because, again, think of people that are talking. There is a conversation, right? And what you have is that, well, someone just finished talking, and then there is, for example, you and Professor Chetna that want to say something, right? So, well, at that point, according to our protocol, you wait for the channel to become idle, and then extract this random time. And unfortunately, you extract the same value. So you start talking at the same time, and remember that our nodes, well, that's a different with respect to human beings, are half duplex. So once they start talk, they do not stop. So you actually start, and what you say overlaps. So who is listening to you cannot decode the information, right? Cannot understand what you two are saying. So, well, that's like extracting the same random time and have a collision between the transmissions. Well, then, nobody understood what you said, so you need to try again and access the channel and repeat what you said, right? So at this point, you stop transmitting, you listen, there is no hack, people did not understand, so you decide to say it again. And this time, you are going to wait for a random time again, and then transmit. Now, what the protocol says is that this time, that is the second time that you try to say something, you should extract this random time in a larger range of values. Why? Well, because now, since you are using a larger range of values, the probability that you extract two different values is higher, right? Because clearly, the shorter the range, and the more likely is that people will select the same value. The larger is the choice, the possibilities, and the lower the probability that you extract the same value. So this time, you get a larger range, and you indeed are able to extract, extract two different values. So one of you will extract the smaller value and will access the channel first, right? So the protocol imposes that if you fail, you double this window for this reason. Because what it thinks is, well, the transmission failed, very likely it was due to collision. We don't know, but very likely it could be due to collision. So just to be safe, next time, let's reduce the probability of having another collision. That means you double the window. So you may say, well, this is good, very smart. The protocol takes care of this situation, of this possibility. Great idea. It is indeed. But if the reason why you failed was not a collision with another signal, what we are doing is enlarging the range of possible value unnecessarily. And this means that statistically we are going to extract a larger value. That means that we are going to wait statistically longer. And means that statistically we are increasing the channel access delay. So, great idea if the failure was indeed due to collision between signals, but not such a great idea if the failure was due to a channel error. In that case, no benefit, and actually you hurt the system because you are going to increase the delay. Okay? So we commented a lot already about temporal fairness, so let me go on because we are a bit late. Block acknowledgements. Well, that's another issue that I would like to mention because it is indeed quite useful. We said that whenever we have unicast traffic, we need to have acknowledgements from the receiver. And we also said that when a transmitter gets hold of the channel, it's going to use the channel for a given time, okay? The transmission opportunity. Now, this means that if you have several packets to transmit, you can do that because you have your transmission opportunity and you can use all the time interval that has been assigned to you. So you can transmit not just one packet, but several packets if they fit in. Now, if this happens, you should transmit one packet after the other at a very short distance in time, so one next to the other. And the time interval that separates these packets is very, very short. It's called sieves. It is very, very short. Now, at the end of the transmission opportunity, you should request for an acknowledgement, a so-called block acknowledgement, because in this case, well, what we are doing is, well, I finished, and at this point, you receiver can send me the acknowledgement back. And the acknowledgement that I request is a block acknowledgement. It means an acknowledgement that refers to all packets that I send. That says basically if each of these packets have been received successfully or not. This is a quite important, let's say, enhancement with respect to regular Wi-Fi. Because in regular Wi-Fi, what you have is that for each packet that you transmit, you should expect an acknowledgement. Now, you could do that also here, but clearly you are wasting resources because the overhead will increase significantly. Think of having for each packet an ACK. This means packet, time interval, acknowledgement, time interval, packet, time interval, acknowledgement, and so on. So you are wasting resources, basically. If instead we have this block ACK that is only one ACK at the end, and inside it includes the information related to the outcome of all packets that I sent, well, I'm going to make the communication much more efficient. So this is another aspect of this communication protocol that has been improved with respect to regular Wi-Fi. So the last piece of information about this MAC protocol that I would like to give you is how you resolve internal contentions. Let me go back to the initial, sorry about that, if I go back by several slides, but the initial picture so that we can explain better and more quickly the concept. So here we had these 4 queues. Now, hopefully we understood how each queue behaves. And this means that they will use their own parameters in order to contend for the channel and transmit a packet. It means send a packet to the physical layer. But remember we said each queue behaves as an independent transmitter, right? So this means that these queues are not contending for the channel only with the other queues that are in the other vehicles. They contend for the channel also between each other. So what happens if 2 of these queues decide to transmit a packet at the same time? Well, clearly there is the so-called collision, but is this a real collision? Because we are within the same MAC layer, okay? We are not at the actually sending the packet over the wireless channel. We are still inside, let's say, the vehicle radio interface. So this is a virtual collision because the vehicle radio interface can solve the collision internally. And the way we'll do that, well, it will be through a simple scheduler here that when we have two queues that try to send their packets to the physical layer, it will solve the collision by saying only one packet goes through, and that packet will be the one associated with the queue with the highest priority level. The other queue, the loser, will treat this situation as a normal collision, a normal failure, and so it will prepare to retransmit its own packet. While the highest priority queue will actually go through, so for that will not have any failure, and the packet will be actually transmitted. So that's a virtual collision that is solved internally within the vehicle radio interface. Okay. Now, let me go back to the slide where we were. Okay. And you find the explanation, of course, in this slide for your record. So this is how it works. And as we were commenting actually during the break with one of you, this is the current standard that has a lot of many advantages. And mainly it is simple and it is cheap. The technology itself, indeed, for those of you who know how regular, let's say, traditional Wi-Fi work, well, it is very simple and very similar to the Wi-Fi protocol. So even the device that you have, the radio interface that you have to develop to implement this MAC is it's well known how to realize the device itself. So the cost is extremely low compared to other technologies like CV2X, when we'll have boards for CV2X as well. So these are great advantages. But at the same time, we have some shortcomings or points of attention that we should look at and possibly improve. So one issue is basically inherent to the protocol itself. This is based on carrier sensing multiple access. It's based on contention. So we cannot have deterministic guarantees on quality of service. It's true that we have different queues with different priorities, but the actual delay that you obtain for the transmission of a packet cannot be deterministically determined. So this is a significant weakness if we have target requirements as the one that we stated at the beginning. And in particular, CSMA-based schemes, well, they work fine when the traffic load is not too high. If there are too many transmitters that try to access the channel, well, then the probability of collision among the transmissions is very high, and the throughput of the system clearly goes down. So is this approach suitable for our use cases? Well, it really depends, right? It really depends on the use case and on the condition, as we were saying at the beginning. If you have a situation, an urban environment with very high vehicle density, and there is a sudden break-in by the vehicles, several vehicles, that generate therefore simultaneously alarms, and these alarms need to be transmitted with very low latency, well, then it means that we have many transmitters contending for the channel at the same time, and unfortunately, this protocol, as we said, will not perform so great. So this is indeed one of the main issues. And consider that when we have the target values that we stated at the beginning, like 3 milliseconds to 150 milliseconds, those are for autonomous vehicles in particular. If you think of using radio interfaces and communication for traditional cars, like the one that we have now, well, you could do that. You could add an OBU, a radio interface, to our vehicles. That's called retrofit. You can do that, vehicle retrofit. That is, equip existing vehicles with this new device and enable communication between these vehicles. That can be done. But our vehicles have got human drivers, right? So if you want to have applications that assist the driver, well, then you have to account for the fact that human drivers have got a reaction time. They need time to react to an information in a brake, for example, or turn, or whatever the maneuver is. So this reaction time of the human drivers is not negligible. As you can see here, well, on average, we can consider about 1 second as a reaction time. It depends clearly on the individual, and so we cannot have a deterministic value for everybody. But anyway, it's of the order of 1 second. So, well, you can have applications that assist drivers, but considering that there is this quite large time that is needed to the driver to act, well, the communication needs to be very efficient. That means that even in this case, you can allow maximum hundreds of milliseconds, no more than that, in order to let the service work efficiently. Because if you sum this with the reaction time, then the time left to take action is a short one. So through this technology, basically the goal is not to achieve 3 milliseconds, as we said for autonomous vehicles. Is more around tens or hundreds of milliseconds. Still, this protocol cannot guarantee you that you are going to achieve this delay. Okay, so that's a weakness of this technology. So you may wonder why nobody has proposed other schemes, right? For example, based on TDMA. In that case, you will have a deterministic guarantee in terms of quality of service, or CDMA, other technologies that you can use at the MAC layer. Well, the reason is that, for example, for TDMA, you need first a very fine, refined synchronization among the nodes. And as we said, GPS currently is unable to guarantee that all vehicles will have such accurate synchronization. Also, in order to implement TDMA or CDMA, you need often a centralized scheme. That is, there must be someone that assigns the time slots or the codes to be used for transmission. Otherwise, if you do not have this centralized entity, central entity that does that, well, you can still implement these kind of schemes, but you will need a contention phase all the same. Okay, so it is not easy to design an efficient scheme based on TDMA and CDMA. So that's why the standard currently still is based on CSMA. Okay, this is the best, all considered, that they could have. Now, other issues that we should consider, take into account. So let's consider the case of unicast traffic, unicast transmissions between vehicles. Well, in this case, similarly to what we have in Wi-Fi, this standard as well tries to include access mode that helps to avoid collisions, but it works only for unicast traffic. And this mode implies the transmission of additional control packets. It works like that. So let's consider two vehicles, let's say A and B, that want to communicate. A wants to send data to B. So what we can do is the following. A, before sending the data packet, what it does is, as usual, listen to the channel. Assuming that the channel is idle, it will first transmit a control packet that is called request to send, RTS. And this packet is intended for B. When B receives this data packet, if it receives the RTS correctly, then it will send back a second control packet that is called clear to send. That basically means, yes, feel free to send me data. I'm available, I'm ready to receive it. And then, if A receives the CTS correctly, it will send the data packet, and the data packet, if this is successful, will be acted by B. Now, why is this potentially better than the other mode, the simpler mode that we introduced before? Well, because in this case, if you think about it, by using RTS and CTS, we are sort of reserving radio resources for this data exchange. Why? Well, because when A transmits the RTS reports as a destination B, but can be heard by all other vehicles that are neighbors of A. So all other nodes that are there and that will receive the RTS as well will say, okay, there is a dialogue that will occur very soon. So I'm not going to access the channel because someone else is going to use the channel. So they will refrain from transmitting, they will be silent. So basically, through the RTS transmission, we block all the neighbors of A. Then, when B receives the RTS, if it receives correctly, and send back the CTS, what happens is that the CTS will be heard by all its neighbors. So what we do is, well, these neighbors are now blocked, because here in the CTS, they will realize that there will be a dialogue very soon, right? So they cannot access the channel. So if this exchange of RTS and CTS is successful, the result of it will be all other nodes here will be silent, and all other nodes here will be silent. So when A transmits the data packet to B, that's protected. Nobody is going to interfere with that transmission because all these nodes and all these nodes are blocked. Okay? So in this way, we can ensure that the data, unicast data transmission, is actually protected and will be likely very likely successful. So this might be a good idea, as I said, but what is the disadvantage? Well, clearly we have more control packets, right? So the overhead of the protocol increases, and we are going to delay the data transmission even more. So it's good on a way, and it's bad in the other way, right? There are always pros and cons. And clearly, as we said, it can be done only if it's a point-to-point communication, so it's a unicast traffic. If we have broadcast traffic, RTS, CTS cannot be used. Why? Because in that case, we do not have only one destination, we have many destinations. So if you send the RTS, who is going to reply? Well, they cannot reply because all of them should, and clearly their replies will collide, so it's not possible. So this means that broadcast transmissions cannot be protected in any way. And unfortunately, for safety traffic applications, in many situations, we need broadcast transmission. Think of alarm or warnings. Well, they should be sent broadcast, right, to many vehicles, all the vehicles that are in the area. So typically, safety applications rely on the transmission of broadcast messages. And in this standard, they are not protected and not protectable. So that's another weakness that we have. Now, that said, let's look at the higher layers. Here will be quicker because the higher layers, let's say, imply fewer details. And they are, let's say, from a certain point of view, let's say from the communication point of view, less interesting. As we said, the higher layers now are labeled through the 1609 number that identifies the documentation, the standard documentation. I would like also to mention that still in the US, there is another association that is the SAE that defines especially at the application layer, some messages that could be transmitted through the protocol stack of WAVE. So this may be another source of interesting documentation. However, while the IEEE standards are open if you are an IEEE member, so typically in universities you have access to all IEEE documents if the university has subscribed to that. I don't know if IIT Kharagpur has got, but I guess, right, they have the subscription. The SAE instead, you have to, of course, to pay to get the standards, and typically universities do not subscribe to SAE, so they are harder to acquire. For the higher layers, as we said, we will also look at the ECE contribution. But let's start with the WAVE higher layers. So first of all, the upper MAC. So what does the upper MAC? Well, the upper MAC takes care of channel coordination, because we said that in general we have this super frame. The super frame is divided into two phases, one for control channel, the other one for service channel. Remember that control channel means that on that channel we'll send, from the application point of view, the messages related to safety. Okay, so the important messages, the most important messages that everybody should receive. While on the service channels, that are many, so it's not positive that all vehicles will listen to the same service channel at the same time, right? So in those channels, you still have application messages, but let's say less important. They are not safety urgent messages. So in general, we have this division, but actually we can have different time synchronization. So for example, even if the default values is to have 50 milliseconds for the control and 50 milliseconds for the service channel, you can actually change that, right? And you can configure the use of the possible channels at this upper MAC. So you can develop your own algorithm in order to manage the transmissions on the different channels. So this is what you do at the upper MAC. And I would say that is the most important function for this layer. The standard that is related to the upper MAC also defines three possible modes of operation for our nodes. And in particular, we have the possibility for the vehicles to have continuous channel access. That means some nodes, for any reason, could be a roadside unit or it could be a vehicle, continuously operate on one channel only. For example, vehicles could choose to operate always on the control channel. That means to basically have only safety application messages and to be there all the time, right? A roadson unit could be also working on a service channel continuously if it's there to transmit other types of traffic like commercial services. The other possibility, of course, is to alternate between two channels, and this is the default mode, so control service, the basic one that we already mentioned. The third possibility is to have immediate channel access. That means, for example, you are on the control channel, and then you receive the advertisement, the message, the control message that we introduced at the very beginning talking about the architecture. So you receive this advertisement message of the BSS by the BSS initiator. And in this channel, there is written also the different applications that the BSS supports and on which channels they are supported. So you read, for example, of a very interesting application on a certain service channel. And what you can do if you adopt this mode is to jump immediately on that channel because you want to access that application immediately. So this is possible if this mode is set at the upper MAC layer. So that's called immediate channel access. Of course, you can do that also if you are in a service channel. You hear this advertisement that reports another application in another service channel, and you want to jump into that service channel as well. Then we have the upper layers that we said they are on the left. You have the traditional UDP, TCP, and then IP at the bottom, and the new module, the new layer that is the wave short message protocol. So I guess that you know already how more or less IP, TCP, and UDP work. This is the new block that we have there. Why did they introduce this new protocol? Well, to make simple to make the system simpler, because in this case you can deal with short messages, as the name says, more quickly and in a lighter manner. So this means that we'll have handled by our block the management frames, and the management frames are the advertisement that we introduced already. The advertisement are generated by the BSS initiators, and they are always transmitted on the control channel. Okay? And this is an example of messages that are dealt with by this new module that is the short message protocol. Then other types of packets that we can have in our system are the data packets. And the data packets actually can be classified as IP data frames. And these IP data frames are dealt with the usual stack IP, TCP, UDP, and they should be always transmitted on service channels. Or they can be data packets but short, and in this case they are going to be dealt with the new block, the short message protocol, and they can be transmitted either on the control channel or on the service channel. Actually, the standard also provides some instructions on which kind of message applications should be transmitted on the control channel and on the service channel. Now, these packets, as we said, are dealt with by this new block. That means that they will have a lighter encapsulation. So they still have a header that is attached to the packets by our new module, but this header is shorter, and you do not have the double header of IP and TCP, for example, or IP and UDP. You have only one header and a small one. The goal is indeed to reduce the overhead, because most of these packets that are dealt with the short message protocols will be safety packets, application related to safety. So we need to be quick and to reduce the overhead of the system. And that's why they introduced this new block. So make things simpler, as we were saying. Now, we said that the criterion based on which packets, data packets, are dealt with by the IP, TCP, or UDP, or the short message protocol is the size, right? Which size? Well, the rule is that if the packet size is larger than the MAC layer maximum packet size, then well, what you have is that they should be dealt with IP, TCP, UDP. If they are smaller, they should be dealt with the short message protocol block. Security. We are not going, of course, into the details of security, but I would like just to mention that there are specifications 609.2 for security. So there is the possibility to have a secure communication link between vehicles and between vehicles and the roadside unit. In particular, you can provide confidentiality, meaning that using public and private keys combined with symmetric keys, you can actually make the transmission confidential so that only the receiver will be able to decrypt the content of your message. Another important issue is privacy. So they are working, of course, there are many proposals in order to provide privacy to the users. That means that your ID should not be revealed. So if you are a transmitter and you transmit a packet and information, of course you need an ID, but through pseudonyms you can actually protect your real ID so that nobody can track you as you move, and therefore you guarantee privacy to our users. Importantly, from May 2018, all car makers will have to obey to these regulations that are called GDPR, so General Data Protection Regulation, and this is an international rule. So this regulation includes all the instructions so that the privacy and the confidentiality can be provided. And if you are interested in security and in this field in particular, this is very interesting because this is new and all car manufacturers are working in order to meet these new regulations. So it's very, very relevant. Okay, so this is the list of security services that, let's say, we aim at guaranteeing in vehicular communications. The standards do not yet meet all these requirements for all transmissions, but this is what ideally we would like to provide under any conditions in an efficient manner. So authenticity, that means that you should be able to ensure that the sender of a transmission was you. Authorization means that you would like to authorize some vehicles to transmit, to make certain transmissions or to access certain services and others not. Integrity means that you should be able to guarantee that a packet that has been transmitted has not been modified by anyone. So you need some way to be sure that what you receive, it is indeed what was transmitted, and that nobody tampered with that information. Excuse me. Non-repudiation means basically to demonstrate all the previous three to a third party. And confidentiality clearly means that only the receiver should be able to access the information that you sent. As I said, typically these are guaranteed by using public-private key encryption and also a mix of symmetric keys and public-private keys. Why? Because symmetric encryption is light and fast, while public and private keys, let's say, can efficiently provide confidentiality and also authenticity when the information is small. In that case, they are feasible in a short time. Otherwise, they are more complex, so if you have to encrypt a large amount of data, it becomes very, very challenging. So you prefer to adopt solutions that exploit both methods in order to combine the advantages of public-private keys and symmetric keys. But that's about security, so it will need a class per se. We are not going into the details of that. The last thing that I would like to mention about this wave protocol stack, it is about the applications, and this is quite important. That is the definition of the messages that should be used for safety applications. The regulations, the standardization in this context is very relevant within the SAE forum, where they basically defined these basic safety messages. So these basic safety messages are indeed safety messages that should be used for safety applications. They defined only one message, but this message has got many possible fields, and most of them are optional. So this means that depending on what you want to transmit, you can fill in certain fields rather than others. The fields that are, let's say, mandatory, that need to be in this packet, are related to the position, the speed, the direction of the vehicle. Then you can add many other information, as I said, depending on what you want to transmit. According to the WAVE standard, these packets, these basic safety messages, should be transmitted by our vehicles periodically with a frequency of 10 Hertz. So this means that they should be generated one every 100 milliseconds. So if you think of an urban environment with many vehicles, we should have that all these vehicles periodically transmit every 100 milliseconds a BSM. So that's a lot of traffic. Okay, so they do not need to be synchronized, of course. They can transmit at different time instance. The important thing is that each of them generates a BSM every 100 milliseconds. But already you may have quite a traffic load over your channel because of just these basic messages. Now, that said, let's move to the ECE contribution. And this is called ITS G5, as we said. What did ECE do? Well, ECE was late. The US standard already issued several documents. They standardized the lower layers, as we said. So ECE said, well, at this point, it does not make sense to issue another standard for the physical and MAC layer that is again based on CSMA. It has been already done, let's take it. Let's instead try to improve the WAVE standard at the upper layers. And this is indeed what they did. And what they did was to add actually some protocol layers and also to add some functionalities here and there in order to improve WAVE. Clearly, they had, let's say, an advantage at this point because they were late, but they already had the WAVE structure. They had already the guidelines given by WAVE, so they could analyze what was there and identify the weak spots of the wave standard and try to act on that. And among the, let's say, the contribution of the ECE, as we said, new protocol layers, so different upper layer protocols, but also they have like a upper MAC, different channel assignment for services. So they were very precise in defining how these frequency channels should be used for the different applications. And there are actually different specifications for safety and non-safety applications on how to use these channels, and they are the A and B series. So if you are interested in that, the ECE standards are publicly available, so you can actually download them and have a look at them. Now, we were saying that they added a protocol layer and also some functionality. Indeed, they added basically this facility layer, the networking and transport layer, and they made some additions to the access layer, including, as we will see, the so-called DCC. So this picture summarizes what we are going to explain related to the ECE contribution. Let's start with the access layer. What are the improvements that they proposed? Well, what they said was, well, clearly the fact that what WAVE says, vehicles should either operate on control channel or service channel and have only one radio interface. It's very simple, very cheap, but not very efficient. So what we should do, first of all, is to let vehicle operate simultaneously on the different channels. So we should have two radio interfaces, one that operates on the control channel, so we are always aware of what is going on from the safety point of view, and the other that instead works on a service channel. So this is basically the summary of the contribution that they made. And then they also defined new messages. One is, as we will see, very similar to the advertisement message, and the others instead are application messages that are similar to the BSM, but they are actually two different types of messages depending on the condition on what you have. Now, for the access layer, the other thing that they said was, let's improve a little bit the MAC, because as you remember, that's the other weak point of the WAVE standard. In particular, based on the studies that they carried out, they detected the fact that due to these different priority levels of the queues, there are queues that get starvation. That means the low priority queues are highly disadvantaged with respect to the others. So what they said was, let's change the parameters. The access parameters are associated with the different queues and the different priorities, so that this low priority queue get a chance to transmit some traffic. And this is indeed what they did, and in particular they changed the value of CW, the contention window, that is the right extreme of the range of values that you use to extract the random time. That indeed has a great impact on the possibility of a transmitter to access the channel. So they identified that as the main parameter to work with, and they set the values of this parameter accordingly. About the DCC, well, this is the decentralized congestion control. It's the new functionality that they added mainly to the access layer, but it actually spans through all the layers that we mentioned before, so also the network transport layer and the facility layer. what is this? Well, this is another attempt to improve the access, channel access by our vehicles. Why? Well, because as we know, the CSMA scheme will work fine when we have a traffic load that is not too high. But unfortunately, there are conditions under which our vehicles may transmit a lot of messages, the periodic ones, and maybe there is other traffic to be transmitted as well. So what can we do? Well, the ECE tried to address this specific point through this functionality that is called DCC. And in particular, what they did was to classify the status of the channel. So by listening to the channel, every vehicle will be able to see if the channel is in the relaxed state or active state or restrictive state. If it's relaxed, it means that the traffic load is low. If it's active, means that it's acceptable. If it's restrictive, means that we have congestion. So the first thing to do is to be able to detect the traffic load that we have over the wireless channel. Once you do that, so once you know what the situation is on the traffic channel, well, what ECE does is to apply different algorithms. And as I was saying, the main ones act at the access layer, but actually they also span through the other layers that ECE added to the protocol stack. Now, let's look at the main ones, so the ones that act on the access layer. Well, what you can do, for example, is vary the transmit power level. Why? Well, because as we said at the beginning, if you have a rural environment with few vehicles, then you will need someone to communicate with. So you need to extend your radio range in order to find a neighbor, and this means to set the transmission power higher. But if you are in an urban environment with many cars, well, then what you need is to reduce your radio range because there is too much interference. There are too many people there. So you need fewer neighbors. And in this case, you need to reduce your transmit power level, right? That's an example. So depending on the channel state, you actually can set the power level accordingly, okay? The other parameter, just an example, on which you can act is the data rate. This is a kind of counterintuitive. For example, if you detect that your channel is relaxed, so it means that there are few neighbors, traffic load is low, well, what you can do is to use a lower data rate at the physical layer. So this means that instead of transmitting at 27 megabit per second, you can transmit at 3 megabit per second. Why? Well, because in this case, the receiver will demodulate the signal more easily because the data rate is lower. So this means that you will have also extended radio range because nodes that are farther away are able to demodulate the signal correctly. And since the status is relaxed, if your packet lasts for a longer time because you're using a lower data rate, well, it doesn't matter, right? Instead, when you have the restrictive state, so high traffic load, what you should do is to increase the data rate at the physical layer. So transmit, for example, at 27 megabit per second. Why? Well, because in this way, your transmissions will shrink, right? They will last a shorter time, and so you fit in the channel more transmissions because each of them will be shorter. So these are examples of how you can vary the parameter settings at the access layer to make sure that the system still performs well under different conditions. And if you have a restrictive state, Well, by adopting these countermeasures, you can actually try to move toward an active or even relaxed state. Okay. So this is just about more details about how you can detect the yes.
If the channel rate only depends on the channel quality, not the speed of the vehicle, so it may happen that the vehicle will pass and the message will not transmit.
Yeah, so it is actually the channel quality accounts also for the vehicle speed. If the vehicle speed is high, it means that, for example, the Doppler effect will be more prominent. So the channel quality may actually decrease because of that, right? So you may have problems in demodulating the signal because of the Doppler effect. So that is, let's say, included in the signal to noise plus interference ratio that you will obtain at the receiver. This physical layer already accounts for the Doppler effect. So the parameters that are used at the physical layer, like the duration of the symbol of FDM symbols, has been enlarged with respect to the traditional Wi-Fi in order to avoid, let's say, the effects of inter-symbol interference, for example. But this has been done already, let's say, as basic countermeasure at the physical layer. Here, what we are saying is trying to react to the traffic load. So we are at the, let's say, mostly the MAC layer, but of course you can set parameters that relate also to the physical layer, because at the MAC layer you have detected a certain state for the wireless channel. And what you try to do is to change the configuration of your protocol layers in order to adapt and possibly also, let's say, mitigate the harsh conditions in which you are operating. So that's why we were discussing earlier, right? There is this protocol, there is a wave protocol that has got some issues. In particular, when the traffic load is high, then you are really in trouble. What ECE is doing is, well, let's take this protocol because this is already, well developed, widely spread. So it's meaningless to introduce a new solution in competition with what is already there. But let's try to improve what is there by adding some functions. So this is indeed what DCC wants to do. Okay. So there are other parameters on which you can act. I only mention these as examples. But for example, there is also the threshold that you use in order to detect whether the channel is idle or if there is a signal on the channel. That's another parameter on which you can act. So the receiver sensitivity is another one that you can vary depending on the status of the channel. Okay, modulation, coding coding rate are other parameters that you can act on as well. Okay. Any other question? Okay, so these are some details, as I was saying, on how you can detect the status of the channel. So basically, you can move, if you are currently detecting a relaxed channel, well, you monitor the channel. And for example, you monitor the channel for 1 second. You divide this 1 second interval in sub-intervals of 50 milliseconds. And for each sub-interval, you determine whether the channel is busy or idle, depending on what you hear. If the power level that you hear is above a certain threshold, then you detect the channel as busy. otherwise it will be idle. So for each sub-interval of 50 milliseconds, you are able to say, well, this was idle or this was busy. And then if you detect more than or equal to 15% as busy, then you move to active. So now you say the channel is active. And similarly, when you are here, you monitor the channel, and again, if you detect that your sub-intervals were busy for more than 40%, then you move to restrictive. If you are in restrictive, again, you are monitoring the channel, and now you monitor the channel based on intervals of 5 seconds. You divide these 5 seconds in sub-intervals of 50 milliseconds. For each of them, you determine whether it was idle or busy. If it was less than 40% of sub-interval busy, then you move to active, and so on. Okay, so you monitor continuously your channel and determine the status in which you are. Now, as part of DCC, you can also change the MAC parameters. So not just transmit power, the receiver sensitivity, the modulation, the coding rate, and so on, but also the parameters that we talked about before. In particular, we have that depending on the traffic queue, you can basically set the transmission power, the data rate, sensitivity, and the minimum packet interval. That means the intertime between consecutive packets. So how often you, from the MAC, can send packets to the physical layer so that the packets can be transmitted on the channel. So even that is an example, further example of a parameter that can be adjusted. Now, the other sublayer that ECE inserts is the networking and transport layer. Now, this is not so well, let's say, detailed like DCC, the access layer, but it is important because it defines the way packets can be routed in your network composed of vehicles. In particular, it defines these 3 modes. The first one is geo-unicast. So geo-unicast means you have packets that need to be transmitted to a specific destination. The destination is identified by means of its geographical coordinates. So clearly you assume to have GPS in our vehicles, and also you assume to have a traffic server that keeps the position of all vehicles in the area where the service is available. Now, once you know the geographical coordinates of your destination, that can be a roadside unit or another vehicle, clearly, well, then you can route the packets toward this destination by sending the packet to the neighbor that is the closest one to the final destination. So you can adopt a greedy algorithm where at each hop you select as next hop the node that is the closest one to the intended final destination. Okay? It's a simple algorithm that works quite well. Of course, if you know the positions correctly. Geo-broadcast means that you would like to send your packet to all vehicles that are within a given geographical area. So it's a broadcast, but only for the nodes, for the cars that are within that given geographical zone. And clearly, this is important whenever you have alarms or warnings that are related to a specific location or area. So everybody should be informed if in that area. And finally, the topologically scoped broadcast means broadcast transmission of packets for a given number of hops. So in this case, you generate your packet and you specify that this packet is a broadcast one that should be retransmitted, but only up to n hops. Once you have reached n hops, the last vehicle should discard the packet. So the packet should not go beyond that. And this is done, of course, to limit the traffic over the channel. So it's like a time to live for the packet. Now, let's consider now the facilities. The facilities layer is composed of 3 sublayers: the application support, information support, and communication support. So very briefly, also because these 2 are not well detailed by the standard documentations yet. The application support, as the name says, is clearly in support of the application. So it takes care of service management, also positioning, because GPS positioning is an application, and security. So for the application, the support that they provide is, as we were saying, the definition of messages. Important messages like the CAM. This is Cooperative Awareness Message. If you like, this is similar to the BSM that the US defined, but now this is transmitted typically with a lower frequency, that is 1 Hz, means all vehicles should generate a CAM and transmit the CAM periodically, 1 every second. Okay? In some situations, they can increase it to 10 Hz, so 1 every 100 milliseconds. But typically, the periodicity is lower than in the US. This is a message that carries position, speed, heading, acceleration, many other optional fields that you may include, like the type of vehicle that you have, if it's electric or fuel, the plate number, the intended route, many other fields that are optional can be there. And then a second message that instead is generated only upon events. So, for example, there is a car accident or a car breaks suddenly, and then you generate this message, this decentralized environmental notification message. So one is periodic, the other one is upon event. This is the main, let's say, difference. As I was saying, the CAMA is the basic one, the periodic one, and it has many additional fields. One important one is also timestamp, so the time reference. And then another optional, but still important for the security point of view, is the digital signature. So the CAM can be signed. Let me say also that, as we said, in some cases it can be transmitted more often than once every second, and in particular once every 100 milliseconds, as we said. The standard specifies the conditions under which you can increase this generation frequency. In particular, it says that if your heading is changing too much over a short time interval, then you have to generate this CAM basically more often than once every second. And the same if your position changes too fast. And the same if your speed is too high. So there are certain conditions that have been identified as, let's say, risky, dangerous conditions under which vehicles should make this message generation more frequent. The other message, the decentralized environmental notification message, is, as we said, similar, but it is not periodic. It is generated on event and reports about specific situations. It gives you the possibility to specify the location to which this information refers, the coverage, that means whoever receives this message should, if specified within the message itself, rebroadcast the message. And typically it determines the geographical area within which this message should be retransmitted. So basically, typically this message should be treated as a geocast. Okay? Also, it reports the cause for this notification, what is the event about, and also when the event for which a notification was sent ends, so there is no danger any longer. Well, you can also have this type of message to cancel the alarm that you previously sent and notify the cars that there is no such risk any longer. So let me go on because these are just details. The other message that ECE defined, as we said, is similar to the wave announcement. So as the announcement reports the information about the basic service set, in particular the applications that are supported and the service channels on which these applications are supported. About security, I don't know if you have any knowledge about the use of encryption, but for those of you who know something about encryption, also ECE foresees the use of public-private keys. So you know that in this case, when you have private-public keys systems, you need certificates, right, that associate your identity with a pair of keys, one public and one private. Now, using private and public keys, you can provide authentication and you can provide confidentiality. And also by using digital signatures, you can provide integrity for your messages. So you meet many of the requirements that we listed before. But you need to guarantee also privacy, as we were saying. So the ECE standard specifies about security the use of these pseudonyms that are basically names, address, that you can use without revealing your identity. Clearly, these pseudonyms should be assigned to a vehicle by either the infrastructure, like the mobile operator, or the car manufacturer can also give you a set of pseudonyms and therefore basically certificates that you can have, that you can use. So when someone wants to talk to you, of course it needs your certificate in order to use the proper key to send you confidential information. But since we want to guarantee privacy, this guy should obtain the certificate that is associated with one of your pseudonyms, so that it will not acquire your real identity. And in this way, we let vehicles communicate and still guarantee privacy while providing also confidentiality. So I know that if you are not familiar with public-private key encryption, this must be a little bit obscure. So in case, just forget about it. But security is indeed an important issue, as you can understand, in vehicular communications, because we have safety issues here. So we cannot allow security attacks. There are people and we need to guarantee, of course, their safety. So false information and attacks are a big danger for our connected cars. Now, if you are more interested, of course, you can read the documentation, the ECE documentation. This is the number, the reference number of the standard. Now, about the information support. The information support is about building maps. So it's something that we already mentioned before. Remember the use case for the intelligent navigation of our vehicles. Well, this will be very important, in particular for autonomous vehicles, because it's the layer that takes care of building the electronic horizon for a vehicle. So it's about combining the information locally at the vehicle and the one that we receive from others in order to build your own map. And finally, the communication support. Well, the communication support is not well defined at all right now. So the specifications are very lacking right now, but the goal of this layer is actually very important. So it would be interesting to look at the documentation in a few years, because the goal here is to support different radio technologies. So have let's say a layer that will be able to deal with different technologies that are used at the lower layers and guarantee applications that work independently of whatever you have below in your protocol stack. So harmonize basically whatever you may have below in order to guarantee that an application can work under any conditions and to guarantee interoperability between cars that may actually use different lower layers technologies. So it's very, very relevant, because you know that whenever we need to develop applications, one of the main challenges there is the fact that you have to have an interface, an open interface with whatever is below, so that your application can be widely adopted independently indeed of the lower layers technology. So this is very important in order to, let's say, allow the development of automotive applications that can work anywhere and in any vehicle. So let me just give you, to conclude, an outlook on what will be the evolution of the current standard. First of all, let me still consider let's say WAVE or 802.11p, the lower layers of the WAVE protocol stack, and see what we expect will be the next evolutions for that. Well, I would summarize that through 2 points. One is the use of MIMO for communication. The other is the use of millimeter waves. Why? Because if you compare the targets that we set at the beginning, remember the 3 milliseconds, 150 milliseconds, gigabit per second as the data rate, and if you think about the current standard that we explained today, well, there is clearly a gap, right? Our current wave standard, not even with the ECE enhancements, can achieve the initial target performance that we stated. So clearly, there is a lot of work to do. What we have today is actually something that we can apply, because the DSRC boards are available. So we can use that to start developing our applications. That's really good. But they're not enough to reach such high performance as it will be required. So they have realized that clearly. And for example, the IEEE Standardization Institute has said, well, we need to perform some innovations, enhancements, significant enhancements, starting from the physical layer. So what they have done is to just form new working groups whose activity has not been reported yet in any documentation, but we know that they are working on the introduction of MIMO and the introduction of millimeter wave communication. Why? Because MIMO as you know, allows you to have several transmissions in parallel by using not just one antennas, but array of antennas. So now if you have an array of antennas at the transmitter and an array of antennas at the receiver, what you can do is basically to establish, let's say, communication between pairs of antennas in parallel. So the same bit rate that you had between one antenna, the transmitter, and one antenna, the receiver, well, you have to multiply that by the number of pairs of antennas that you get. Now, clearly, the difficulty here, the difficulty is to maintain these channels between pairs of antennas independent, and so that they do not interfere with each other and so on. But if you are good, well, then you can really multiply the bit rate by the number of pairs that you get. So this means that if before you had 3 megabits per second, now if you have 8 pairs of antennas, well, then it's 3 times 8. And if you have massive MIMO, that means many, many antennas, well, then clearly you can increase by a factor of hundreds. Okay? So that's a way to increase the bit rate. So if our target was gigabit per second, well, through MIMO, we can actually get there. It is not easy because our nodes are moving. It's a mobile environment, so it's very, very challenging. But the technology will allow that. The second thing is millimeter wave. So millimeter wave means actually working at 60 gigahertz. Okay? So millimeter wave means very, very high frequencies. 60 gigahertz is a lot. And the problem is that at such high frequencies, as you know, then the signal propagation becomes very challenging. So if you want to ensure communication at such high frequency, you need beamforming. So you need to create basically beams over which your communication will be performed that point to the destination node. And the destination node, that is the receiver, will have a beam through which it will be able to receive. Why do you need beams in this case? Because making beams instead of omnidirectional transmissions, well, implies that you will concentrate all your power along one direction. And concentrating power along one direction means that your signal along that direction will be very strong. Strong enough to reach successfully the receiver, even if you are working at 60 gigahertz and the propagation is very, very harsh. Propagation conditions are very harsh. So the trick there is, okay, let's move to very high frequencies. We can ensure communication there, provided that we form these beams, right? So one thing is to adopt beamforming. Fine. Beamforming is already there. We know how to do that. But in a vehicular environment, if you have these mobile nodes, and if you want to have this communication between two nodes, and the two nodes are moving, it means that you have continuously steer your beam so that the transmitter and the receiver beams will be still aligned. Otherwise, if you don't do that, by moving, clearly one beam becomes disaligned with respect to the other. So you need to do that with low overhead. And this is very, very challenging. So enabling millimeter wave communications between two vehicles is still to be done. How to do that in an efficient manner? Well, that's research, open issues that we should actually address. And the same for vehicle and infrastructure, but this is slightly less challenging because in that case we have only one mobile node, while the other one, the roadside unit, is fixed. So it's slightly less challenging than vehicle-to-vehicle communication. Now, the new physical layer for our technology that will work at millimeter wave is 802.11px. This is the name of the working group that is basically has been established to work on this specific issue. So keep an eye on these specifications while they will be available, because they are going to be quite interesting. And before that, look at scientific papers that try to address this specific evolution of the technology. Clearly, by working at 60 gigahertz, so millimeter waves, the advantage is that there we have a lot of spectrum. So instead of 10 megahertz of frequency channel, we'll have large frequency channels and therefore enable very high bit rates. Okay? So the target for latency and bit rates will be fulfilled, hopefully, through the evolution of the current technology toward this PX. And here in the slides, you will find a few more details. Not many are available because the industrialization actually is still to be done. Yeah, please.
On 60 gigahertz also the network coverage will decrease due to the huge path loss.
Exactly, but it depends on the power that you concentrate along the beam, right? So the fact that in millimeter wave you have a reduced radio range, well, in general that's true, but all depends on the kind of beam that you are able to establish. If the beam is very narrow, then you concentrate your power along that direction and you are able to reach quite a distance. Of course, if there are obstacles in the between, then you are in trouble, right? Because line of sight is much easier than non-line of sight with millimeter waves. But in many applications, like vehicle-to-vehicle for neighboring vehicles, if they need to exchange sensory data, and they are vehicles that are along the same road, then you can assume that they are in visibility, line of sight with respect to each other. So that would be, in that case, easy to do for your vehicles. And as we said, since there, those frequencies will have frequency channels that are much wider, then you can really achieve high bit rates and be able to exchange these sensory data, so gigabit per second that we mentioned before. So the other question that we had at the beginning was what is the best choice between the cellular, let's say, technology and the DSRC technology. Now we know what DSRC is and what it allows and so on. Well, who is going to be the winner? Still, we don't know, okay? Because it's true that cellular V2X allows for many things, high performance, but still, as we said, is costly. And still, we don't have the boards. Qualcomm actually is going to develop these boards. It seems that they have some initial versions of the boards, while instead the DSRC is already there in the current version. We don't have yet millimeter wave. We don't have MIMO, massive MIMO for vehicular communication. So we'll see what we get out of these evolutions for DSRC. This is Qualcomm. What Qualcomm says for the cellular V2X is that it's very promising. So to tell you the truth, Qualcomm is pushing very much toward cellular V2X. Okay? Even if it's a US company, and traditionally US was in favor of, let's say, DSRC, because it was also the only technology available a few years ago. So now this is debatable, but this is the evolution for cellular V2X that Qualcomm envisions. So you can see that there is the current release, 14 and then 15. and these will be for high throughput, low latency broadcast only. And then they envision further releases, release 16 for also unicast and multicast traffic with excellent performance that they claim they are not achievable through the DSRC. But as we said, the evolutions of DSRC are still to be seen, and therefore we still need to see what we get. Others actually say that the two technologies will coexist. And actually we'll have CV2X for autonomous vehicles and for high quality of service, while instead traffic safety, starting from the current vehicles, if we adopt vehicle retrofit, will be likely using 802.11p, and we use these technologies to provide these, let's say, more basic but important services. So in this case, really, the future will be a combination of the two technologies. So we are done for today, and thank you for your attention. Tomorrow there will be Professor Chetna Singhal, and then I'll see you the day after with SDN, NFV, and basically the core network of 5G. So if you have any questions, please.